right. Good afternoon. Any question? Yes.
Are you doing close solutions to the previous page? So we're using the right code for.
The code, you mean?
Yeah.
I'm gonna post it to them. For homework 9. Alright. We are gonna talk about kinematic synthesis. It's gonna be for the rest of semester, I guess. If we have time, we'll start talking about common follows. So, kinematic analysis versus kinematic synthesis. In kinematic analysis, this is what we have done so far. You are given with a mechanical mechanism like 4-bar mechanism. The length of mechanism are given. So you have your mechanism, you have the mechanism in your hand. We are doing displacement velocity and acceleration analysis. And last topic that we covered was force analysis. So these are the kinematic analysis. What is the kinematic synthesis? You are given with a desired task. So given desired task or motion or desired can be prescribed. So in any case, you would like to generate, to design or synthesize a mechanism such that it's generating the desired task. So you don't have anything, so no mechanism is given. You start from scratch, you are going to design the mechanism such that it's generating that task for you. It can be, for example, you would like to design a mechanism such that it's moving this box from this position to this, from this position to this position, and this position. It can be a desired task that you want to design a mechanism such that it generates this task for you. Or you have a point P, and you would like to design a mechanism such that it's moving along this desired path. So you are given by a path, and the point P is supposed to move along this path. So you would like to design a mechanism such that it's generating that path. So this is a definition of kinematic synthesis. In kinematic synthesis, it has two parts. First, type synthesis. What do I mean by type synthesis? You are given with the desired task. You look at the desired task, and you should do these things. First, type of members. Do we need to have linkage mechanism? Do we need to have gears? Do we need to have cams? So based on the desired task that you are given, what kind of members do we need to have? So we are doing this. Suppose it's a linkage mechanism. Find the degree of freedom. Based on the desired task, what should be the degree of freedom for the mechanism? It should be 1 degree of freedom, 2 degree of freedom, or more. What else? Number of links. How many links do we need? And joints. So we should do this as well. And type of the links. Do we need binary? Do we need ternary? Or combination of them? What kind of links do we need to generate the desired task? So after you answer this question, you go to the dimension of synthesis. So 2. So once the type synthesis is completed, we are doing the dimensional synthesis. What do I mean by when I say we are done with type synthesis? We know that we have a linkage mechanism. It's a 4-bar mechanism with 1 degree of freedom, for example. So we need 4 binary links and 4 pure rotational joints. So after we figure out the type of the mechanism, we are doing the dimension of synthesis. We determine the size of the links. Basically, we are designing the mechanism by sizing the links, and we will be done after this step. So in this course, we just deal with the dimensional synthesis. We assume that the type synthesis has been done, and we have a linkage mechanism. We don't cover CAM. If we have time, we go to the CAM follower. And the degree of freedom, number of links and joints have been determined, so we are going to focus on sizing the links. And after you size the links, you can make that mechanism. So we classify dimensional synthesis to 3 categories. In dimensional synthesis, we are going to have 3 types of the problem. 1, function generation. Function generation problem. 2, path generation problem. And 3, motion generation. So we are covering these 3 categories of dimensional synthesis. So let me go one by one. What do I mean by function generation? Then we go through the path and motion figures. Consider this 4-bar mechanism for this slider crank with no offset. If you remember, I said usually the input link is going to be this guy, and the output link is link number 4. Typically, we put the motor here. It's going to run the input link, and the output link is the link that we get the output. And in slider crank, usually the input link is this guy, and the output link is this slider. So if you are given in kinematic synthesis, you are given with a desired task. So if the desired task is representing correlation between input link and output link, we call it function generation. So if this angle, for example, is theta and this angle is phi, if you are given by this problem, design a mechanism such that when theta is at 30, we would like phi be at 95 degrees. And when it goes to 42 degrees, I would like this is changing to 105. And when it's at 68 degrees, I would like this at 118. So if the desired task is given by correlation between input link and the output link, we call this problem function. For slider crank, the input is the angle of link 2, which is the input link, and the location of the slider is S, is going to be the output. So if SI theta I, if angle is at 30, I would like SI be at 3.8 inch. When it's increasing to 45, I would like this at 2.1 inch. And when it's at 60 degrees, I would like this at 1.5 inch. So if I give you something like this, you can simply say it's a function generation because we have been given by a correlation between input and output. So path generation is simple. You are given by the coordinates of one point, and you would like point P is moving along these coordinates. When X is at 2.5, Y is at 3.6. When X is at 1.5 is 3, and when it's at 1.2, you would like this at 2.8. So we are given with the coordinates of one point, and we would like to generate or to synthesize the mechanism such that it gives us that desired motion. So function generation, path generation. What would be the motion generation? This is about moving a point. Motion generation is about moving a rigid body, not a point. There is a box that I would like to be at this position. Then this box should be moved to this position and this position. So we are given with the desired motion of a rigid body, and we would like to generate a mechanism such that to give us this motion. In this case, you look at the rigid body and pick a line, for example, this line, or any line, this line. I pick this line. And one point on that, coordinates of one point on that line, this point P. So then I follow the line with the point of P on the new location. So this line has been moved to this position, and this position. So since we have rigid body, we need to have orientation and orientation of the rigid body in this three position, and also a location of one point. So what we are given the angle of this line with the ground is 90 degrees here. So theta is lambda, whatever. Lambda is 90 degrees on the first position. On second position, the orientation of this, for example, is changed to 120 degrees. And here it's almost 180 degrees. And x of point P and y of point P, here, for example, it's 5 and 1. Here it's 4 and 2 and 3, and right here it's 1 and 4. So you are given with the coordinates of one point of the box and orientation of one line. So these types of the problem is called motion generation. Basically, we are tracking a motion of a line in the rigid body. This line can be any line in this rigid body, because if this line from here to here, it has been rotated by 30 degrees. If you pick this line, it's a different line. If you pick this line here is going to be this. From here to here also you have rotated by 30 degrees. So it doesn't change the amount of rotation. So any line can represent the orientation of rigid body. This slide is going to describe function, path, and motion duration. Here we have xi, yi, and beta I. Let me change it to beta. X and y component of a point. I define 3, it can be more or less. Here I just wanted to have these 3 desired location, but it can be more. Question on this. Now let me talk about precision point or key precision point. Yeah, suppose point P is supposed to move along this path, this desired path that you would like to generate that one. So it's a path generation because we are given with the motion of one point. You designed the mechanism and come out with the dimensional synthesis. You make the mechanism. This is X, this is Y. And then run the test, and you will find that the actual motion is going along this path. This is a desired path or desired motion, desired path versus actual path. So the point which they have intersect, we call them precision points because we easily could pass through those points. So we call these precision points, and precision points. And the structural error can be defined the difference between actual points and desired points. So for example, at this point, at point x1, I was supposed to get this y, but I got y prime 1. So at x1, instead of getting y1, I could generate y prime 1. So a structural error is defined as y1 minus y prime 1. y1 minus y prime 1. So I will get error here for point x1. For this point, for precision point, I could guess that the error should be 0 because it's a definition of precision point. Precision points are the points which they match on the actual path and desired path. So at this point it's going to be 0. At this point, for example, this is y2. This is y prime 2. This is y2. y2 minus y prime 2 is going to be negative, something like this. So we do So it's kind of error shape for this mechanism. At precision points, it should be 0. These are the precision points. Error is 0. And the other points that you might have some errors. One of the homework problems that you will see is asking you to find the structural error for a given design problem. It's going to be homework 11, I believe. Any question so far? Alright, now I'm going to look at some example of function generation, path generation, and motion generation. If you look at this metering device, it's kind of analog metering device. So this is a box, a black box. You don't see inside the box. Here, these arrows is moving along this, and this arrow is moving along that. So when this guy is at x1, this one should show you y1. And when it goes to, for example, x2, it should move to the y2. So it's kind of metering device. What is going to happen inside the box? You are going to have a forward mechanism that you don't see. And this forward mechanism is going to generate this desired function for you, or this desired task for you. It's kind of function generation because you are given with a correlation between input link, which is this angle, and the output link, which is the angle of this one. So this is the example of function generation. One group 3 years ago chose this as a project. They designed a metering device to generate this function, y equals to ln of x. So this guy is representing x, and the other side is representing the natural logarithm of x. So they sized the linkage such that it generates this desired task. This is another example for function generation. This is the carburetor mechanism. This is accelerator pedal or gas pedal, and this is the carburetor. There is a mechanism between which connects the carburetor, the gas pedal to the carburetor, such that when you push the gas pedal by 15 degree, the number is 15 degree, the carburetor should be open by 20 degree. And when you want to speed up, you are going to push more, so you are going to push by 25 degree. This should be open by 40 degree. So you would like, and at the meantime, the middle link should move by 10.5 for the first position and 17 degree for the second position. So we would like to design a mechanism such that it generates this desired function. It's a function generation because we are given the correlation between input angle or input link, which is this, and output link, which is the carburetor. So one group design this mechanism. This is a gas pedal that you can see. If you, the red color is just showing the angles here. When I'm moving from the first arrow to the second arrow, I'm gonna move by 15 degree. If I do that, here the carburetor is gonna move from first arrow to the second arrow, which is 20 degree. If I want to have, if I want to speed up, I push more, so the carburetor is gonna go to the third position. Third position. If it's the first, from the rest, going to the second, and third is going to the last. So that was a project that one group did. This year, one group can pick this one. We just change the numbers, and you can try to design a 6-bar mechanism. It's a 6-bar mechanism. One 4-bar here, and totally 6. One is ground, 2, 3, 4, 5, and 6. This is example for path generation. I already talked about path generation. These are the coordinates of point C. I have point P that we would like to generate to come out with a 4-bar mechanism such that it's moving along these 3 coordinates of point P. So this is kind of I'm gonna do this class activity. So what would be the difference between moving a point P through the 3 position, this is point P, and moving the box through 3 locations? So what would be basically, if I give you these coordinates, why do I need this column? I need this column because we have rigid body and orientation matters for rigid body. So this point, when it's moving from this position to this position, the rigid body can have different orientation. I keep this point here, but I can rotate it about that point. So for that reason, I need to have location of one point and orientation of one line on that rigid body. So here I have conveyor 1, conveyor 2. So the box coming, this mechanism should be designed such that it can pick up the box from here. It should move it to this position, and it's gonna rotate it by 180 degree from, or 90 degree. 90 degree. From this position to this position. So we are gonna size this linkage such that it generates that desired motion for us. This also can be a project if any group is interested to do that. this is a cabinet with the shelf. We would like to design a mechanism such that it's moving the shelf from this position to this position and this position. So since we are interested in moving of the rigid body, it's a motion generation. So it's kind of motion generation. And in this one, point C, we would like to move along this desired path. So since the motion of moving a point is given or is desired, it's going to be path generation. Now, if we look at this one, it's a water or philometer device. So it's measuring the level of water. So link 2 is going to be here. It's a water, so you can just put the measuring link to the water. And this guy is representing or is showing the level of water. So for this desired task, what do we have? Is it function generation or path generation or motion generation? Is it representing the correlation between input link and output link, or is it talking about moving a point, or is it about moving the desired motion of a rigid body? It's a function generation because we are connecting this link, because this one is going to show us the level of water. So we are going to connect the motion of location of this guy, the location of output link, which is the link 2 and that mechanism. So it's a kind of function generation problem that we discussed in this mechanism. So let's start with, after this, let's start with a graphical approach or graphical method for synthesis of, we are doing for synthesis of a 4-bar mechanism for function generation and motion generation. So the goal is synthesis of a 4-bar mechanism where we have function generation and then where we are given with motion generation. So this is the input. As always, it's an input. If the rocker is output, this is rocker. If rocker is output, then we have function generation because the desired task that we are given is correlation between input and output. So it's kind of function generation. If we are given with the correlation between this guy and the rocker. But if we are given with the coupler as an output, if the motion of coupler is given, then we are dealing with the motion generation. The motion of rigid body, which is the coupler, is given, so we are gonna deal with the motion generation problem. We talked about precision point. For a 4-bar mechanism, if we are dealing with function generation, the maximum number of precision points that you can have is 7. You cannot have more than 7 precision points for a 4-bar mechanism when you have function generation. For path generation, it's going to be 9. So if you are going to move point P through the desired position, the maximum number of desired points that you can pass is 9 points. This is a path generation with prescribed timing. What do I mean by prescribed timing is if the coordinates of the point P that you want to generate is given like this, you have path generation. But if you say that when point P is at this location, I would like the input angle be at 20 degrees. If you restrict or connect the location of point P to the input angle, we call this path generation with prescribed timing. So you would like point P be at that position at prescribed time. So if you are given with this column, it's a path generation with prescribed time. So if this is the case, the maximum number of precision points that you can have is 5. And if it's a motion generation, you can have maximum 5 precision points. I will start with the function generation for 4-bar mechanism. Question so far. So this is the desired motion or task that you would like to generate. I would like to design a 4-bar mechanism which is driven by a constant speed motor with 45-degree rocker. I will talk about equal time forward and backward, but it says it should be crank rocker. So this is the crank, this is the rocker. So the rocker, when the crank completes 360, the rocker oscillates back and forth. It has one extreme here, another extreme down there. So we would like to have 45 degrees for the range of rocker. So the rocker can go over 45 degrees. This is what we want to design. We would like to have a crank rocker. And what do I mean by equal time forward and backward? Meaning, if it takes, for example, 5 seconds moving from this extreme position to this extreme position, we call it forward. The forwarding motion is going to take 5 seconds. The backward motion also, it should take 5 seconds. So when you are moving from this point to this point, it should take the same time. We call them timing ratio equal to 1. We will see later that how can we design a mechanism with timing ratio different than 1. For example, 2, 3, more. So when the forward motion is taking less than the backward motion. So in this problem, we are gonna do it graphically. We are gonna have 5 free choices. Okay. Let me do it on Wednesday class because I don't want to do it unfinished. Any questions about this? All right, we continue on Wednesday.